In this lecture, I want to go over functions. Just give a brief review of the idea of what a function is and working with functions, how to evaluate functions, that sort of thing. So in general, if we have these two sets, x and y, a function is a correspondence between them, kind of a way to relate the two sets. You can kind of think of the two sets as numbers. So it's a way to map numbers from this set to numbers in this set. And what is special about a function is that each member of the set x, so we many times will kind of denote sets, with little circles like this. So each point x in this set gets mapped to exactly one point in the other set. All right, so it wouldn't be a function if I had, for example, a different x. If this same x got mapped to a different y. All right, then it's not a function. All right. On the other hand, if a different x got mapped to the same y, that's not a problem. All right. So that's what's special about functions, is that each x gets mapped to one y and one y only. Different x's can get mapped to the same y, but the same x can't get mapped to different y values. Okay, so let's get away from sets, because that's something that most people are less familiar with thinking in terms of, and let's talk about a couple equations. So one example of a function is y equals x squared. All right, so we can look at this function. Graph looks like this. All right, and notice that for each value of x that I can choose, there is only one value of y. All right, so there's an x. Here's another x value right here. Has a y. It's only one y value. Call it maybe x0, x1. I don't know. This could be x2. It has its own y value. So anywhere across here, each x value is associated with only one y value. I will again point this other point out, though, that for any, at least with y equals x squared, because it has this y-axis symmetry, that if you draw a horizontal line here, that this same y value would be associated with this. Here would be another one. Maybe call it x3. This y value, x0 and x3 might have the same y value. That's not a problem. All right, it's still a function. But the main thing is that for a given x value, you can only find one y value on the graph. All right, or in a table or any other representation that you like. So that's an example of a function. An example of something that's not a function is x equals y squared. So that takes this and kind of turns it on its side, right? So like this. All right. So for example, if we're out here at 4, the x value of 4 would be associated both with the y value of 2, but also with the y value of negative 2. So that makes it not a function, because both the point 4, 2 and 4, negative 2, right? Now here, for example, if this were equal to 2 and x3 were equal to negative 2, then I would have the point 2, 4 and the point negative 2, 4, not a problem, right? Because 2 isn't associated with any other y value. Negative 2 is not associated with any other y value. Even though the different x values just have the same y, that's not a problem. Here, the same x is associated with two different y values. That's when it's not a function. Notice then that if I were to draw a vertical line through here, it would hit two different spots. All right? That indicates, that's why the vertical line test works, to tell if we have a function or not, is because if it hits in more than one spot, then the same x value is associated with two different y values. So here, the vertical line test works, right? Every x value only has one y. That is the defining property. The other thing I'll say, the x values, or along the x-axis, that is our domain. We call that the domain of the function. It's Also the inputs, the things that we can put into the function. And then the range are the outputs. So we put an x value in, or an independent variable, we get a dependent or a y value out. So let's look at just a few more examples of functions, and then talk about domain and range a little bit more. All right. So, and also talk about function notation. So here's we have f of x equals square root of x. All right, and that means so our input is here, and then the input would go here. So for example, if I wanted f of 4, that's going to be the square root of 4. Whatever I put in here, I put it in here. So that's 2. So let's think about what the graph of this would look like. This is just a quick sketch. All right, but whether you look at the sketch or look at the equation, let's think about what the domain and range of this would be. So the domain, what are the types of things I can put in for which this function is defined? So it would have to be, first, any positive number would work, right? I can take the square root of it. It might not be a perfect square, but I can still find it. I can approximate it using a calculator. So x could be positive. And we can also take the square root of 0, because 0 times 0 is 0, so the square root of 0 is 0. So that includes 0. X, notice x cannot be negative, so that's not part of the domain. So it's only x values that are, well, we could take the square root of a negative number, but it wouldn't be a real value, a real number. And we are talking about real valued functions here. So we put real numbers in, we want to get real values out. So that's an important restriction that we have on the functions that we're working with. So in that case, the domain is only positive numbers. Now, if I take the square root of any number that's greater than or equal to 0, what kind of numbers will that give me? Well, that will give me non-negative numbers out as well. Okay, so there's an example. A different example could be g of x equal to cosine of x. All right, so g is the name of our function. This is the name of our independent value. We could just as well have called it g of t equals cosine of t. So t is now our independent variable. The graph of this looks something like this and continues in both directions forever, right? So I kind of gave away the domain, right? It's going to be all x, which is sometimes we denote that r for all real numbers. We can go along the x-axis, and anywhere along the x-axis we will find a y value associated with it. Notice here this stops. So on the other side there are no x values associated with this graph. In terms of the range, well, this goes up to 1 and down to -1. That's it. Unless we were to multiply by some number to stretch out our amplitude, then the range goes from -1 to 1. All right, so those are just a couple of examples of common functions and thinking about what it means to find the domain and the range of those. We have to think about what we can put into the function and then what types of things we would get out of it. We can use that just by thinking about the function, using the algebraic, or we could also graph it. The only limitation with graphing is that obviously when you graph something, you don't see the whole function, you're just seeing part of it. So you still have to think about it a little bit. But the graph can certainly help. Okay, let's just talk about evaluating functions again. So let's say I have a function, call it the square root of x plus 5. All right, so this notation is useful because it allows us to kind of think of inputs as just replacing the x here and replacing it here. So if I do f of -4, that's going to be -4 plus 5, which is the square root of 1, which is 1. So notice here we can put a negative in because we're adding 5 before we take the square root. Here the domain would be any x values greater than or equal to -5. -4 is bigger than -5, so that works. How about if we do f of 11? Again, we just replace x with 11. That's the square root of 16, which is 4. F of -8. DNE does not exist. Remember, the domain has to be greater than or equal to -5. If I put in -8, I end up with the square root of negative 3. That is not a real number, so we say that the function does not exist at that value of x. Graphically, we could see that this is going to go down to negative 5 here. It's going to look just like the square root of x that we had before, except it's shifted over to negative 5. All right. Now to get a little silly, what is f of smiley face? Well, it's just smiley face, the square root of smiley face plus 5. This is just to emphasize the idea that whatever you put in here, you just replace it there, and that's how we find the function, evaluate it, whatever that is. So, for example, if I wanted to find f of x plus delta x, well, I'm just going to replace my x here with x plus delta x plus 5. All right, and why would I put in such a thing? I mean, smiley face actually makes more sense than this, right? Like, where is this coming from? Well, we have something called the difference quotient. This will become important as we get into calculus, and it's defined this way. We take f of x plus delta x. Delta x is just some little increment on x all over delta x. So this would just be the square root of x plus delta x plus 5 minus the square root of x plus 5 all over delta x. How we might simplify that and what it means we'll talk about later, but for right now the important thing is that we know how to take something, even if it's something we can't simplify or maybe don't fully understand kind of what it means initially, but we can just take it and replace it. Go ahead and just put it in there. Okay. Also want to mention just a little bit about piecewise functions. All right. So a piecewise function is one that is defined differently along its domain. So for example, we could have f of x equals x squared plus 2 when x is less than or equal to 1, and 2x squared plus 2 when x is greater than 1. All right. So again, we're basically splitting the domain. When x is less than or equal to 1 along the x-axis, it's going to have one. This will be one way to get the y values. It'll be a different formula to get the y values when x is greater than 1. So, for example, f of negative 2. Well, negative 2 is less than 1, right? So this would be negative 2 squared plus 2. That's just going to be 4 plus 2, or 6, right? F of 0, we are still less than 1, so I would use this one. 0 squared plus 2, that's just 2. F of 1, again, still here, because this is when x equals 1, I'm still using this one. It's only when I get greater than 1. Next, anything bigger, I would use this. So for f of 1, I would have 1 squared plus 2, which is 3, but if I had f of 1.1, then I would use this one. So it would be 2 times 1.1 squared plus 2, which off the top of my head I don't know what that equals, but the point is anything bigger than 1, and now I've jumped over to this one. One function that we see quite a bit of that can be defined in a piecewise way is the absolute value of x. All right, so graphically, absolute value, it looks like this, right? Remember, absolute value just it's basically the distance from 0 on the number line of any number. So if I put in 3, well, 3 is 3 from 0. If I put in negative 5, I get 5, because negative 5 is 5 units from 0 on the number line. Another way to think of it is if I put in a positive number, I just get back the same number. If I put in a negative number, I get back the opposite. So the way to define this in a piecewise manner, though, is this is the line y equals x when x is greater than or equal to 0, right? So if you look at this, it actually looks like the line y equals x, but it's going to be the line y equals negative x when x is less than 0. So over here, I have the line y equals negative x. So, of course, if I were to continue this, it would kind of keep going this way, and this one would keep going this way. But I've restricted the domain, so I'm only going to use this part when x is greater than or equal to 0, and I'm only going to use this part right here when x is less than or equal to 0. All right, so that's kind of another way to think of how the absolute value function can be defined. Okay, just want to talk about some common functions that you should be familiar with, kind of classifying those functions. So some types of functions. First, we could have algebraic functions. And these are functions of the form f of x equals x, g of x equals x squared, h of x equals x cubed. We were talking if we could have a j of x, square root of x, because this could be written x to the 1/2, right? So basically anything that you can take x to a power of. Also any combination of these, right? So 5x to the 4th minus 3x cubed plus 8x squared minus 3, for example. Just any combination of these is called a polynomial. All right, where we basically just take powers of x and coefficients and combine them, and that gives us a polynomial. These are all algebraic functions. Also, rational functions are algebraic. All right, rational, the way I think of this is ratio, right? It's the ratio of two polynomials. So, for example, I might have x squared minus 3x plus 4 over x to the 5th minus 3x squared minus 8x. Anything where I take the ratio of two polynomials. It could be as simple as x minus 1 over x. It could even be as simple as 1 over x. I guess I should add to this the constant function, right? So if I have something like f of x equals c, where c is a constant, right? For example, like f of x equals 1, right? It's just a horizontal line at y equals 1, all right? These are all considered algebraic functions. Then we could have another class of functions are trig functions. All right, so this could be something like sine and cosine and tangent. Recall that the tangent can be defined as sine over cosine. All right, secant, which is 1 over cosine. Cosecant, which is 1 over sine, and then cotangent, which is 1 over tangent. Since that's basically the reciprocal, we could also write it as cosine over sine. All right, that's another class of functions. And then a third class of functions are can't spell, logarithmic and exponential functions. All right, so that would be something. So logarithmic, you could have natural log of x, you could have log base 2 of x, you could have log base 10 of x, or more in general, log base b. All right, we'll talk about these more when we get in a later lecture. We'll talk about these in more detail, but just, these are functions you should have seen before. We'll talk about their properties more in another lecture. So these are logarithmic. The exponential would be things like e to the x, 2 to the x, 10 to the x, more generally, b to the x. Okay, so these are kind of some basic functions that you should be familiar with. But how do we get more functions out of these? If we're familiar with these basic functions, we can transform them, right? So in other words, we could take f of x plus c. So let's let c be some positive number. All right. So this would take some f, something like this. All right. And if I add a plus c to it, then it would shift it over. So it would look kind of exactly the same, except we would shift it over this way. All the points would be shifted by c. So it shifts everything to the right. All right. If I have f of x minus c, then again I could have something like this, and then in that case I would get shifted over to the right. Did I say to the left here? I think I did. But anyways, we shift to the left. One way to think about this is in order to get the same y value, I need to move the x value in order to get the same y value, right? So here the original y value was at 0. In order to still get 0, I need x to be smaller. Here I would need x to be bigger, so it shifts it. It's a little counterintuitive, but we're shifting this way when we subtract c. Right? The whole thing is shifted that way. The ones that are maybe a little bit easier to think of are f of x plus c, because we're just going to take now, this is going to be, so these are horizontal shifts, right? This is a horizontal shift to the left, this is a horizontal shift to the right. So if I kind of take my same, similar looking function, if I add c, then I would just move it up, right? So it would look the same way, except it would get shifted up by c, because I'm taking basically all my y values and adding c to them, so I just move each point up by c. Finally, if I have f of x minus c, then you can probably guess what's going to happen here, right? Haven't used purple yet, so the whole thing is going to just get shifted down, all right? So everything gets moved down by c. All right, so these are just ways that we can transform the basic functions. I mean, these kind of basic functions that we should be familiar with, we can create new functions out of these functions by transforming them. And we could do a combination of transformations, but this is just a quick reminder of how the original function would be related to one of these transformations. Okay, last thing that I want to discuss, I believe it's the last thing I want to discuss, is an idea. It's actually related to something we've talked about already in terms of symmetry. The idea of odd and even functions. All right. So we say a function is odd if f of negative x equals negative f of x. In other words, if I make x negative, it makes y negative. All right. So this is basically just origin symmetry. If the function has origin symmetry, then it's an odd function. So in terms of symmetry, we said if xy was on f, then negative x, negative y is on f. All right. So an example we've already seen is x cubed. The way we check it is we check for f of negative x. We put in negative x, and let's see if we get negative f of x out. Or negative f of x would be negative x cubed, right? So if I put in negative x, I get negative x. I cube it, that indeed gives me negative x cubed, right? And that's negative f of x, since x cubed equals f. That's negative f, all right? So again, the symmetry with the origin looks like this. Another common function that has this property is cosine of x, all right? So anyways, so that's all I want to say about the odd function. In terms of the even functions, we say a function is even if f of negative x equals f of x. All right, so this is y-axis symmetry. Because what we're saying is if we put in negative x, we get out the same y value. So in other words, if xy is on f, then negative xy is also on f. The example we looked at earlier in terms of symmetry, actually I think we looked at the beginning of this lecture as well, was y equals x squared, right? Right, it has y-axis symmetry. If this point here is xy, then making the x value negative results in the same y value. The way we test it algebraically, we say f of negative x equals negative x squared, which equals x squared. But notice that is just our f, right? So f of negative x equals f of x. That is the definition of an even function. Here, f of negative x equals negative f of x. That is the definition of an odd function. The other thing I wanted to point out here, because we talked about this with symmetry, in terms of x-axis symmetry, there are no functions with x-axis symmetry because this would be something with x-axis symmetry. Anything with x-axis symmetry, if xy is on the graph, then so is x negative y. But this would mean that the same x is associated with two different y's, right? Anything that has x-axis symmetry wouldn't pass the vertical line test. So we had three types of symmetry, but only two of them apply to functions. The origin symmetry is associated with odd functions, and the y-axis symmetry is associated with even functions. And that's all I'm going to talk about with, this is just kind of a brief overview of functions. So that's it for this lecture.